Find the limit using L'Hopital's rule if necessary. We have the limit as x approaches 4 of x squared minus 16 over x minus 4. When we plug in 4, we get 16 minus 16 over 4 minus 4. We get 0 over 0, which is an indeterminate form. Since this is an indeterminate form, we can use L'Hopital's rule to evaluate this limit. Limit as x approaches 4 of the derivative of the top is 2x, and the derivative of the bottom is 1. So that's we can plug 4 in now. So 2 times 4, the limit is 8. Over here, let's try to plug 3 in. We get 9 minus 6 minus 3 over 9 plus 6 minus 4. Now the top is 0 and the bottom is 11. So the limit is 0. If we use L'Hopital's, let's say we did use L'Hopital's, and we shouldn't, because the answer is 0. We get 2x minus 2 over 2x plus 2. When we plug in 0, we'd actually get negative 1, and that is wrong. So you can't use L'Hopital's when you don't get an indeterminate form. This is just an answer. It's 0. Students will be able to find limits using L'Hopital's rule. Use L'Hopital's rule to find each limit. Let's plug 0 in, and we get sine of 0 over 0. And sine of 0 is 0 over 0, so that's an indeterminate form. We can use L'Hopital's rule, so we get limit as x approaches 0 of 3 cosine of 3x over 1. So now when we plug in 0, we get 3 cosine of 0, which is equal to 3 times 1, or 3. Let's plug pi over 2 in. We get 1 minus sine of pi over 2 over 1 plus cosine of pi when we take 2 times 1/2. So that's 1 minus 1 over 1 minus 1. So we get 0 over 0. We have the limit as theta approaches pi over 2 of negative cosine of theta over negative 2 sine of 2 theta. And we're going to plug pi over 2 in. So we get negative cosine of pi over 2 over negative 2 sine of pi. Cosine of pi over 2 is 0 and sine of pi is 0. So we get 0 over 0 again, which is another indeterminate form. And I forgot to note that we're doing L'Hopital's rule here. Now we can take L'Hopital's rule again. We have the limit as theta approaches pi over 2 of, let's see, we get sine of theta over negative 4 cosine of 2 theta. And I just took the derivative of the top and the bottom here. And then, yeah, that'll end up being, yeah, everything's right. Now we can plug in pi over 2. We get sine of pi over 2 over negative 4 cosine of pi. And that's going to be 1 over 4. 1/4. I want to discuss the graph of secant of x, cosine of x, tangent, natural log, and inverse tangent. So here, this is well, if the wave, if this is sine, then this must be, actually this is cosine. This is cosine. So anywhere cosine is 0, we're going to have a vertical asymptote. So this is secant of x, and we notice that the limit as x approaches pi over 2 is positive infinity from the left, and the limit as x approaches pi over 2 is negative infinity when we approach from the right. This wave right here is sine, so this must be cosecant. And we can see now this is 0 to 2 pi, so this is pi right here. So as x approaches pi from the left, this function is going to positive infinity. Or even values that we can use, the limit as x approaches pi over 2 is 1. The limit as x approaches 3 pi over 2 is negative 1. So we need to just, we need to know the limits of secant and cosecant. This one is tangent, so the limit as x approaches 0 for tangent is 0. The limit as x approaches, this is pi over 2. Limit as x approaches pi over 2 from the left is positive infinity, from the right is negative infinity. And, other things we need to know. Limit as x approaches pi over 4 is 1. This is cotangent, so this was tangent of x. And this one is cotangent of x. So we could talk about some limits here. The limit as x approaches pi from the left is negative infinity. Pi from the right is positive infinity. So in this section, we're going to be dealing with limits, and we kind of have to know limits of these trig functions. About natural log, the limit as x approaches infinity of natural log of x is equal to infinity. The limit as x approaches 0 from the right of natural log of x is equal to negative infinity. As we approach 0 from the right, this graph goes down to negative infinity. This one right here, this is pi over 2. And this is negative pi over 2. This is inverse tangent. This is y is inverse tangent of x. So as we can say that the limit as x approaches infinity for inverse tangent of x is equal to pi over 2. We can also say that the limit as x approaches negative infinity of inverse tangent is negative pi over 2. Limit as x approaches 0 from the left. Well, the tangent of 0 is 0, and we have 0 in the denominator. So now we have the limit as x approaches 0 from the left of secant squared x over 1, because we're going to take the derivative. So we have I can actually plug in secant squared of 0 is reciprocal of cosine. Cosine at 0 is 1. So this ends up being 1 squared. 1 squared, which is 1. Now it doesn't really matter if we approach this from the left or the right. This one is going to end up being the exact same answer. Use L'Hopital's rule to find the limit. If we plug 7 in, we get square root of 9 minus 3 over 7 minus 7. So we get 0 over 0. So we can use L'Hopital's. We'll make a note that we're using L'Hopital's. Limit as x approaches 7 of 1/2 2 plus x to the negative 1/2. That goes to 0, that goes to 0, that goes to 1. So this is pretty much it. So we're going to take 1/2, the square root of 2 plus 7. So 3/2. E to the 0 is 1, minus 1, and then minus 0 over e to the 0 is 1 minus cosine of 0 is 1. So we get 0 over 0. So now we can do L'Hopital's. I keep forgetting to note that I can use this. Limit as x approaches 0 of 3e to the 3x. The derivative of this will be 0. The derivative of negative 3x is negative 3 over 2x e to the x squared. And then cosine of 0 is 1. So when we plug 0 in, we get 3 minus 3 over. When we plug 0 in here, we get 0 minus 1. So we get 0 over negative 1, and the final answer is 0. Here's a little preview of what we're going to do tomorrow. We're going to find the limit as x approaches infinity of 1 plus 1 over x to the 3x. So if I plugged infinity into this, I'd have 1 over 1 plus 1 over infinity to the 3 times infinity. Well, 1 over infinity, when we're working with limits, is 0. So this is 1 to infinity. That's an indeterminate form. And what we're going to do is let's say we let y equal 1 plus 1 over x to the 3x. Then I can take the natural log of both sides. And that's why we want to set this equal to a function, so we can do this step right here. So we can take the natural log of both sides. 1 plus 1 over x to the 3x. Now we can bring this 3x down in front. Natural log of 1 plus 1 over x. And we've already said that this is an indeterminate form. So we're going to do this. We're going to do the limit as x approaches infinity of natural log of 1 plus 1 over x over 1 over 3x. And now we can do the derivative. Now we can do L'Hopital's. So this is equal to the limit as x approaches infinity of 1 over 1 plus 1 over x, then times the derivative of the inside, which is negative 1 over x squared. And then let's see what we got, 3x to the negative 1. So negative 3x to the negative 2. So that's over negative 1 over 9x squared. Now we can multiply the top and bottom by 9x squared. So when we multiply by 9x squared, or negative 9x squared, we get positive 9. So this becomes the limit as x approaches infinity of 9 over 1 plus 1 over x. And now we can plug infinity in. We get 9 over 1 plus 1 over infinity. So we get 9 over 1 over infinity is 0. So 9 over 1 plus 0, we get 9. Well, we didn't start with a function, and we can't really end with this function, because now what we have is natural log. Half of my little tablet here is dead, so it'll just stop writing. Natural log of y is equal to, we've decided that that's 9. Well, we have to undo the equation that we have. So we're going to get rid of this natural log, and to do that we need exponential. So the answer is e to the 9th power.